host, Nick Jikomis, and today I'm speaking with Dr. Judith Curry. Dr. Curry is a climatologist and the former chair of the School of Earth and Atmospheric Sciences at the Georgia Institute of Technology. Her research interests have included hurricanes, atmospheric modeling, air-sea interactions, and a variety of other areas in climate science. She runs Climate Etc., an online blog focused on climate science, and she's also writing a new book called Climate Uncertainty and Risk, which she described towards the end of our conversation. We touched on a variety of topics related to climate science, including the ways in which Earth's climate has changed over time and how climate scientists actually measure this, what computer models are in climate science and what their strengths and weaknesses are and how they're used by climatologists, tropical storms and severe weather events and how these have changed over time. We got into CO2, methane, and other greenhouse gases and how abundant each one is and how impactful each one is in terms of climate change. We talked about different forms of energy such as oil, natural gas, solar, wind, and nuclear power, how she thinks about the trade-offs between different energy sources in terms of their abundance and environmental impact and costs and other factors, and just, how to start to think about all of the trade-offs and complexity there. And we also got into the politicization of climate science and why certain branches of science are especially prone to becoming politicized. So if you're interested in climatology and climate change and how that type of science is actually done in comparison to experimental laboratory forms of science and how all of that works, this will be an interesting episode for you. This is definitely not my area of expertise, so I asked a lot of very basic questions and learned a lot about this subject because I really don't know that much about it. And as always, if you enjoy the content I'm producing on this show, please like, share, and subscribe, whether or not you're listening to the audio version on Spotify or Apple Podcasts or somewhere else, or the video version on YouTube. You can also subscribe to my free weekly newsletter at mindandmatter.substack.com. You'll stay up to date on upcoming guests and topics. I will alert you to some interesting research going on that I'm reading that informs the guests I'm going to have on and the things I'm thinking about, as well as other interesting things that I'm watching or reading and other content I'm producing on other channels. This episode is supported in part by the Amino Company. They specialize in making science-backed amino acid products that you can mix into any drink. Their products contain a mixture of essential amino acids, the building blocks of proteins in the body, as well as other nutrients including minerals like iron and electrolytes like potassium. Your body is constantly repairing damage, and your muscles and tissues need the right mix of amino acids and nutrients to do this effectively. One thing I like about Amino Co. is they actually conduct clinical trials to determine what their products really do. They have a variety of formulations engineered for different purposes, and my personal favorite is one called Heal, which has been shown to be 3 times more efficient at triggering muscle growth and repair than other protein sources. It helps maintain healthy inflammation levels and preserve muscle mass during periods of inactivity. I mix this product into the water bottle I bring to the gym and consume it before, during, and after my workouts, and I have felt a noticeable difference in my performance during those workouts and my recovery times from soreness and fatigue afterwards. Their products are keto-friendly, soy-free, vegetarian or vegan, gluten-free, and non-GMO, so they are compatible with almost any diet or lifestyle. You can support the podcast and try Heal or any of their other products by using the discount code MIND when you visit aminoco.com/mind. You will get 30% off your purchase. If you work out regularly or do intensive exercise, I recommend trying AminoCo's products. I get a lot of companies reaching out to me about advertising, and I only end up using and liking a small percentage of the products that I see. So check out aminoco.com/mind and use the code MIND to try these products today for 30% off. Today's show is brought to you in part by Dosist, an all-natural cannabis company specializing in dose-controlled cannabis products made with plant-based ingredients. To learn more about Dosist, their products, and where they are available, please visit their website through the link in the episode description. And with that, here's my conversation with Dr. Judith Curry.
Earth sciences, geology and geography, meteorology, atmospheric science, stuff like that. By the time I graduated, I had gravitated more towards meteorology and the atmospheric sciences. And then I went to graduate school at the University of Chicago in the Department of Geophysical Sciences. So again, I continued with the broad background in the geological sciences, but again, focused on the atmospheric sciences. And my thesis was on Arctic, the radiation environment of the Arctic. And I took the typical academic pathway. I did a postdoc for a few years and then had my first faculty position was at Purdue University. Then I moved around quite a bit. Every few years, I got a better offer, try something new. So I moved quite a bit. So I had faculty positions after Purdue and Penn State, and then University of Colorado Boulder, and then at Georgia Tech, where I was chairman of the School of Earth and Atmospheric Sciences for 13 years. I left Georgia Tech in, I think it was 2016. It was a little bit of a premature retirement. I was just getting really tired of the whole academic scene. It was not, what I signed up for way back when. It was getting, politicized in early days of cancel culture. And I said, no, this is just not what I want. So I left, and in about 2006, I had started a company, Climate Forecast Applications Network, which applied research, to real world problems. And once I retired, I amped up the company, and that is now what my full-time job is. I'm president of the company, and we do a range of things, sort of applied problems related to weather and climate, mostly extreme events. And we can probably talk about some of that later in the conversation. I entered the public debate on climate change inadvertently in 2005. So I was co-author on a paper, and you may remember this. It was published a couple of weeks after Hurricane Katrina, and we found that the percent of Category 4 and 5 hurricanes had doubled since 1970, and so that made quite a splash. And we weren't really talking about a global warming angle, but I immediately got adopted by the climate change advocacy community, and they really liked this issue. And then I started seeing I'm not sure I like what's going on here. This is really politicized and tribal, and it's not really promoting, objectivity in the science. So I backed away from that quite a bit. And I started playing around in the blogosphere, trying to, explore that mode of communication and education. And I inadvertently landed on Climate Audit, Steve McIntyre's blog, which is the leading skeptics blog. And I found that it was, really interesting to participate in those discussions because they wanted the data, they wanted to analyze it, they wanted to, discuss a lot of details and say, okay, well, this is quite interesting and challenging, and it helped me hone my communication skills. Then in 2009, and this was the other big sort of change in direction. As a result of ClimateGate, this was the unauthorized release of presumably a hacker of emails from the University of East Anglia. It involved a lot of IPCC authors, and it showed a lot of behind the scenes skullduggery that I thought reflected very poorly on the climate community. And I started speaking out publicly about how climate scientists need to behave better. They need to make all their data and everything available publicly. They need not to denigrate skeptics or people who disagree with them, but engage with the serious people and try to see if there's anything you can learn or at least defend your point of view. You just can't ignore them. And the other thing that I introduced at that time is we need to pay a lot more attention to uncertainty. We're way overconfident in what we think we know about this problem. And so, I thought these were, motherhood and apple pie kind of sentiments, but the mainstream climate community thought I was the Antichrist for saying these kind of things and for breaking solidarity, with the people. And so then I really got sort of sucked more into the public debate. And in 2010, I started my own blog, Climate Etc., judithcurry.com, which is still active at this point, although I don't quite post as often as I did in the early days. So at this point, I'm working for my company. I engage in the public debate to some extent, but at least most significantly for me, I'm in the final throes of completing a book, Climate Uncertainty and Risk, which I hope to submit by the end of August. So that's my story in a nutshell.
Excellent. Well, I'm going to ask you a lot about climate science, which is definitely not my area of expertise, but it's something important that I wanted to learn more about. And because this is such a big issue and for better or worse, a controversial subject, I was hoping just to, start picking people's brains about this area at a very high level. Can you talk about what climate science is and how the tools and methods of climate science compare to, say, experimental fields of laboratory research where you can do controlled experiments?
Okay, when I started graduate school in the late 70s, there was no such thing as climate science or climate studies. If anything, climatology was a minor subfield in geography, where you just collected data and did statistics. Atmospheric science was really the main discipline that people would study to, understand about the dynamics of climate, and then subsequently oceanography became more interested in the longer time scales, and then chemistry became involved, geochemistry, atmospheric chemistry, and then land surface processes, biophysics. And so this started to encompass, a lot of what I would call traditional scientific fields, geology as well, with paleoclimate. So there were a lot of traditional scientific fields that were dancing around the climate problem. Now, in atmospheric science, this is really like it's applied physics and applied chemistry, basically. I mean, that's the foundations of atmospheric science. But again, once you get into climate science, at least the physical science part of it, broadly defined, you're bringing in biology and geology and chemistry, biogeochemistry, and so forth and so on. So there's quite a lot of scientific disciplines that feed into what is now regarded as climate science. Now, the climate system is a very complex system. And by complex, I don't mean just complicated. Complicated means there's a lot of stuff, but all the causal relationships are fairly well defined and understood. Once we have a complex system, then there's all sorts of crazy feedbacks, and small triggers in one part of the system can be amplified in other parts of the system. I mean, you've got something, very complex going on. There's emergent phenomena. And so what I would call the physics of the climate system in its complexity more resembles systems biology and economics because of this complexity, rather than physics and chemistry with its laboratory controlled experiments. And again, we're even though people think they can control the climate by dialing up carbon dioxide or dialing it down, well, it's a lot more complicated than that. So, the best we can do is try to hope we're thoroughly observing everything that we need to or want to observe. And then we test out theories and ideas and hypotheses to try, with data. And climate models are an important tool for trying to understand. It sort of integrates a lot of our knowledge, within these global climate models. do you have any specific questions before I dive into, what climate models are and what they're useful for and what they're not useful for?
Oh, no. I mean, that's where I was hoping you would go. I mean, so,
Okay.
I come from a laboratory science background, and I'm used to doing, experiments in the lab where we can really isolate
Right.
single variables and test cause and effect. With the climate, you can't really do that. You have to go out and, make as careful measurements as possible and certain observations of this, some subset of this very complex system. And then I always hear about climate models and these models and the forecasts and predictions people make from them. So I'm hoping you can just describe for us, like, what are these computer models? What goes into them? What comes out? And how do we evaluate how much
Okay.
weight we can give them?
Okay. Well, global climate models, and they're now called Earth system models once you bring in, a lot of ocean geochemistry, atmospheric chemistry, stratosphere, and whatever. So Earth system models, it includes like the same kind of atmospheric dynamics that drive like a weather forecast model, and the same thing for the oceans. And then there's a land surface module, where, the biomass actually responds to the weather. They've got interactive land surface models. You've got sea ice module, you've got ice sheet modules, you've got atmospheric chemistry modules, all of these things, lumped into one giant computer program with all these interactions. And so a lot of this, in the early days, climate models were tools to help scientists organize their knowledge and to test ideas, help refine our questions, and test some ideas and run some experiments and test our understanding and pose some what if questions. Well, if we do this to the ocean surface temperature, then how do the clouds respond? There's thousands of questions that you can ask with these climate models. But when the IPCC, this is the Intergovernmental Panel on Climate Change, really was spinning up, starting in the 90s, the climate models developed an authority in the policy sphere and really became a focal point for funding and for scientific research. The idea is they wanted to make these models good enough where we could predict the climate, not just global temperature, but also the regional climate variations, whether you're going to have, floods or droughts, in the Pacific Northwest or whatever. And this hope for the climate models that you could use them for predictive purposes was never realized. In fact, the climate models, even if you run them out and say, well, how much global warming, the average global surface temperature will you get? Well, the climate models diverge greatly. Their sensitivity to increasing carbon dioxide really varies by a factor of 3. So, that hasn't been nailed down. There's a lot of disagreement about what this climate sensitivity is. And until recently, the IPCC just took the values from the climate models. Now, with the latest round of climate models, with more sophisticated aerosol cloud interactions and whatever, the climate sensitivity has exploded into values that are generally regarded to be way too high. So this is making people, okay, well, what are we doing with these climate models? We can't, it's not helping us narrow down the climate sensitivity.
So what I'm hearing is, when you say climate sensitivity, what I'm hearing when I hear you say that is that, when we make these models, climate scientists have to they have to bake in some variables about how sensitive certain aspects of the climate, like the atmosphere, say, are going to be, or how easily they're going to respond to changes in CO2 levels, but that these numbers aren't known quantities that are measured in nature. They're things that we have to estimate or guess about.
Okay, well, it's even more complicated than that. Climate sensitivity to CO2 is an emergent thing from the climate models. It's not something you directly tune. It depends on the big uncertainty is the clouds, how you're modeling the clouds, and the clouds are small scale. So these are parameterized. So it's not real physics that's driving the cloud interaction with the climate. It's these parameterizations, and you can change these cloud parameterizations and end up, with pretty different values of climate sensitivity. That's it in a nutshell. So it's not the 10 years ago, there was a lot more tuning of the climate model to give you the answer that you thought you wanted. Okay. More recently, the climate modelers have been a little bit more honest in terms of just letting the models do what they're going to do. That said, that they do throw out certain versions of the model that they don't like the answers to. So people are increasingly recognizing that these climate models can't be used to tell us anything about the climate sensitivity to CO2. So people are falling back on, historical observations, paleoclimate observations, and then just physical process reasoning to help us narrow down the values of the climate sensitivity. But we're still dealing with a factor of 3 uncertainty in this most fundamentally important parameter. The recent 6th assessment report from the IPCC really downplayed the climate models quite a bit. They were talking about, they didn't use the climate models for climate sensitivity, and they used these simple climate emulator models, with climate sensitivity as an input or something like that to drive their economic impact models and whatever. So, I feel like that this latest IPCC assessment report in many ways has broken the hegemony of the global climate models in the international policy making. These climate models, in some of the lawsuits, climate change lawsuit litigation, climate models have been accepted as evidence. Just if this is a result, this is the evidence, and you don't get to waste any time. It's not waste any time trashing the climate models. So, that I think that's something that's changing beneath our feet right now in terms of what we can actually learn from these climate models. And it's, again, they're not useful for projecting the 21st century climate, certainly not regional climate. It gives you a huge range of uncertainty from scenarios that could be no big deal to, fairly catastrophic. So.
Yeah. Well, one thing that could be useful here is, and I don't know the answer to this myself. So when we think about climate models that are modeling the Earth's climate, like the whole climate of the Earth, and they're making predictions about what might happen in the future based on these models, how can we, can you compare that to, say, just like local weather forecasts? What's the state of the art for local weather? How far out in time can the weatherman or the weatherwoman predict local weather?
Okay. Depending on which models and how you post-process, the model output, and this is something that my company does, but we beat climatology beyond 2 weeks lead time, say for surface temperature. So, there is some pretty significant skill in these atmospheric weather models. The weather models are run at higher horizontal resolution, maybe 5 miles, which is much higher resolution than the climate models. And so they're able to get all the details of the atmospheric circulations that can produce these extreme weather events, heat waves and hurricanes and all that. The global climate models are much coarser, and they don't actually simulate these extreme events. They're really sort of statistically interpreted and massaged, but they're not explicitly calculated. So a lot of this argument about global warming causing or worsening, extreme weather events. I mean, that's speculative, and the climate models don't help you. Again, you have to look at not just at the past 50 years, but you have to look at the past 150 years and paleoclimate data where you have it to try to understand, the regional variability that has happened in the past before you can start drawing any conclusions about what global warming might be doing to the extreme events. So a lot of what people claim, this was made 30 times more likely because of human-caused global warming. I mean, that's, mostly fiction. We don't know. I mean, we can do some simple reasoning and saying, yeah, this could have been worsened a little bit, but, just from simple thermodynamic arguments. But if there are dynamical feedbacks and whatever, I mean, you can't really make these statements with much confidence at all.
And so you mentioned earlier that you had published that paper around the time of Hurricane Katrina around, I think, tropical storm intensity or frequency. And I vaguely remember at this time, I'm like just entering college, but I do remember it being prominently discussed in the media that, hurricane intensity and frequency seem to be increasing over time. Can you bring us up to speed on what we know about that? Is that true?
Okay. Well, it's not hurricane frequency. That's been pretty steady over the records that we have, and maybe even declining slightly. The main issue of concern, and this is the one that was raised in our paper, was the percentage of the hurricanes that make it to category 4 or 5. Okay, we found a doubling since 1970. Well, subsequent analysis showed that the data in the 1970s from satellite just isn't good enough. And it's probably not good enough until maybe 1985. Since then, there's a smaller signal of an increased proportion of category 4 and 5, smaller than what we found. Whether this can be attributed to global warming or whether it's part of a multi-decadal oscillation in the Pacific Ocean. Again, more than half of the hurricanes are in the Pacific Ocean. So whatever's happening there is sort of driving global hurricane statistics. So, we don't know. The jury's still out. Scientists disagree on to what extent the percentage of category 4 and 5 hurricane increase might be caused by human-caused warming. I mean, there is a signal there. There could be a contribution from human-caused global warming, but, that there's still disagreement on that one.
I see. And if there is a relationship there, as I recall, the argument is basically if the temperature of the surface of the water goes up, then in general, you're going to get more intense storms. What do we know about how surface temperatures in the Pacific and Atlantic have changed over time?
Okay, well, the whole thing is more complicated than that. So you've got warming at the bottom and warming at the top. So the warming at the top hampers things, okay? And the warming at the bottom helps. So how these things interplay, in terms of increasing the intensity remains to be seen. But hurricane intensity isn't just about the thermodynamics, the heat. It's about the circulations, the dynamics of the atmosphere. And that depends more on patterns of sea surface temperature, which influences the atmospheric circulations, which then produce the intense hurricanes. So it's just not that simple. Now, the thing about the proportion is interesting because even if the proportion is increasing, the total number of hurricanes would be decreasing. So we don't expect an overall increase in the number of category 4 and 5 hurricanes. That might stay relatively the same. So, again, these are, the IPCC, when it draws conclusions, I think it tends to be overconfident. The assessment made by a larger group of hurricane experts under the auspices of the World Meteorological Organization, I thought was more authoritative and had showed less confidence than the IPCC did on most of the things related to hurricanes and global warming. So, I mean, it's an important issue. And a big part of what my company does is make forecasts of hurricane activity, both on seasonal and on the daily time scales. And our clients are like insurance companies and asset managers and also electric utilities companies who want to be prepared for if they're going to have a big outage associated with hurricanes. So that's a big part of what my company does, is making forecasts of landfalling hurricanes in the U.S.
Yeah, and one thing that you mentioned just a moment ago is you were talking about historical data, and you mentioned satellite data and how it reaches back to the 70s and potentially before that, but it didn't get good enough or have enough resolution until 85 or so. And with that in mind, I'm just curious about the general, and I understand this is sort of a big, complicated question with many different pieces to it, but you hear so many arguments about climate change that center around sort of the notion that, okay, well, the climate's changing now within our lifetimes and within the last, couple of human generations, and humans are probably making some contribution to that. But then other people will argue, well, the climate has always changed and it's always dynamic, and there's these, big cycles that go, that cycle over time. So, like, with all of that stuff in mind, how in general do climate scientists study changes in the Earth's climate since from more than a couple generations ago, before we had all of the satellites and instrumentation probing everything that we have today? How much resolution is there, and how far back in time can we get reasonably robust numbers that have to do with surface temperatures and all of the things that we would want to measure?
Even you think the most basic variable would be surface temperature, and that's actually a tough one. Again, the sampling, and whether you're in a city or a rural region, and whether that changes with time will influence, the temperatures. And there's just a lot of, if you're on a mountain, one side of the mountain will have a totally different temperature than the other side of the mountain, and it's all, even though it's sort of close together. So you've got a lot of, heterogeneity, in the temperatures. People who put together surface temperature climatologies, take it back to 1850, 1860. And of course, it increasingly gets worse the farther back you go. And it's really even more uncertain for the ocean temperatures. The North Atlantic is fairly well sampled, ship routes in the Indian Ocean, they have, but the vast expanse of the Pacific, a lot of people say you don't have really good records prior to 1960, the Pacific temperatures, and certainly prior to 1920. So, the data situation is tough. And once you get into rainfall and some of the more difficult to measure variables, then it even gets worse. So people rely on proxy, paleoclimate, looking at sediments, looking at, ice cores, looking at a variety of things to help in, tree rings to help infer what the climate was before we had good records. The problem is most of those proxies can be ambiguous in terms of what they're actually measuring, particularly tree rings. When I first heard about tree rings, they were measuring rainfall and drought. Okay, and that makes sense. But then with the big hockey stick reconstruction, now all of a sudden they're telling me, well, these are measuring temperatures. Well, we can filter out the precipitation component. I don't think so. And then also tree rings respond to increasing CO2. So, you're convoluting a lot of different things, and you're trying to extract from that a temperature signal. I don't think, not something I particularly have much confidence in. So it's hard, the data, the whole climate change issue is underdetermined by data. There's no question about it. Since 1990, we have some wonderful satellite data sets. But even then, satellites have a finite lifetime. And you have to have overlapping satellites to make sure they're calibrated and whatever. And one of the biggest uncertainties in climate science is what the solar radiation has been in the 1990s. There was a gap between the satellites, ACRIM 1 and ACRIM 2, to measure what the sun is outputting. And that gap occurred because of the Challenger, the disaster, that blew up, and that delayed the launch of the second one. So you didn't have this overlap period. And there's a huge debate in the solar physics community as to, which end of these tails, to interpret. One gives a fairly steady, solar scene, since 1980, and the other one is a more highly variable one, which would make the sun a more important component of the recent climate. So we don't have any way to resolve that right now. I think we have to wait another 2 decades before we have enough data from the current and forthcoming satellites to really resolve, how variable the sun actually is on these timescales. So that's one of the big uncertainties. And that's because we don't have good enough overlap in the satellite data. I mean, it seems like a rather arcane issue, but it has, a lot of significance. So that the satellite data sets are wonderful, and we're getting new capabilities all the time, but the new capabilities are wonderful. They help us understand, but they don't help with this issue of having a long enough record. So, the whole situation is underdetermined by data.
I see. So, one of the things I did plan to ask you about was how the sun's output, just in terms of heat and radiation, changes over time. But it sounds like the answer there is basically that the level of sampling we have of that kind of data isn't very good. And so there's probably a lot of question marks there.
Well, there's a bunch of reconstructions, some are high variability, some are low variability. But the more important thing, that it's not totally about what is called total solar irradiance, watts per meter squared, the amount of heat. There's a lot of solar indirect effects, related to ultraviolet radiation, related to magnetic field issues, related to cosmic rays. There's a whole lot of what is called solar indirect effects on climate, which aren't adequately understood. And, these have the potential to amplify the regular energetic variability by factors, as high as 5. So, it's a potentially important, very important issue that we just don't have a good enough understanding of. So, if we're really going to be surprised in the 21st century about how the climate change plays out, I think the surprises are probably going to come from the sun in terms of, some factors that really aren't included in the climate models at this point.
Oh, sorry, I was on mute. And do we know, I mean, again, I really know nothing about this subject. So, but in terms of solar radiation, and how it changes over time and what those dynamics look like, is it well known that there are sort of rare, big effects that come from the sun over, at least long time scales, like every, on the scale of hundreds or thousands of years, that you can have, big solar flares and things like this that really deviate from sort of the normal patterns that we would see on like a human lifespan scale?
Well, it's reasonably well known to solar physicists. It's not well known to climate scientists, and it's certainly not well known to the general public. In fact, I'm reviewing a book on sun-climate connections, and there's a whole lot. I've been interested in this topic, so I may be a little bit more knowledgeable than the average climate scientist. But there was a whole lot in this book that I didn't know about, and that this is so basic to the climate problem. Like we just need to pay a whole lot more attention to this issue.
And probably the most well-known, publicly at least, the most well-known variable, or the one that's talked about, I think, the most when you talk about climate change, especially human-induced climate change, are greenhouse gases, and in particular CO2. So can you give us just like an overview of like what do we know about how CO2 levels have changed over time since basically the Industrial Revolution, and how do we measure that, and how does that compare to maybe historical levels that we might have records for before that? And what are some of the other greenhouse gases that maybe don't get talked about as much?
Okay, CO2, over geologic history, millions of years kind of thing, there's been some pretty big variations, and we've had, much higher than we have now. But I would say during the last 500,000 years, since we've sort of had ice ages, the CO2 level has been relatively low, and it rises and falls with the ice ages. As the land uptake decreases or the ocean uptake increases, associated with the advance of the ice sheets, the warming or cooling of the oceans, all these kind of things influence the amount of CO2 in the atmosphere. In the current post-glacial, CO2 as measured from the ice core, was pretty stable from the CO2. However, there's other scientists who are more biological, measure the plant stomates and whatever. And they say that they think that CO2 must have been more variable than we currently think it is. That's a minority view, but it's one that we don't quite throw out. But so it was the pre-industrial concentration of CO2 is about 280 parts per million, and we're now almost at 420. So we've increased carbon dioxide by 50%. So we've sort of already conducted half of the experiment of doubling of CO2. Now, so do we attribute all the warming since like the mid-18th century to CO2? Well, not really, because that was the Little Ice Age, which was caused by a combination of solar variability and volcanoes and ocean circulation patterns. I mean, the jury is still out on exactly what combination of those things contributed to the Little Ice Ages. And we started coming out of the Little Ice Age around 1860. That's when we saw the sea level start to rise, the glacier starting to melt a little bit. And that was before fossil fuels, were very significant. There wasn't really, the fossil fuels didn't really accelerate until about 1950. So you started seeing a temperature increase and sea level rise and everything around 1860. And that was, relatively natural, with a boost from the sun, relatively low volcanic activity, and presumably favorable ocean circulations that help the warming along. The warming hasn't been steady. There's a lot of multi-decadal natural variability, but then we do have this slow creep of global warming. Now, the emissions really kicked in after World War II around 1950, but you didn't really see the warming pick up until the 1980s. Okay, so there was a lull between the 1940s and 1980s where temperatures actually declined slightly, even though CO2 was increasing. And people blame this on air pollution, things like that, which to me aren't very convincing, because you saw this going on in the Southern Hemisphere also, where air pollution isn't a problem. So, there's a lot of things that we don't even understand about the 20th century climate variability, where we do have some pretty decent data. So CO2 is contributing. People who blame all of the recent warming on CO2, I don't think that's justified. I think we had a grand solar maximum that peaked towards the end of the 20th century, which was a player. Ocean circulation patterns were favorable in the 80s and 90s, which I think helped boost the warming. And we only had one major volcanic eruption, that was Pinatubo in 1992. So I think those are factors that also help boost the warming in addition to CO2. Okay, with regards to other greenhouse gases, okay, the second most important one would be methane, which has natural geological sources, but methane, it also has human sources as well. Agriculture has boosted methane production, notably rice and livestock. Oil and gas exploration ends up leaking methane into the air. So those are two big sources, but the variability of methane has been weird. It was pretty flat through the 90s, and then all of a sudden a big uptick around 2006. And it doesn't, trend with anything related to fossil fuels. It may be more related. See, methane is reactive in the atmosphere. CO2 is pretty inert. Methane's reactive. So it may be the reactants, that have been modified rather than the actual emissions of methane. So that's a topic that, there's some debate on and a lot of uncertainty about. Okay, then we have the hydrofluorocarbons. Remember the CFCs that were destroying the ozone? Well, they came up with a whole new set of chemicals, hydrofluorocarbons, which don't have the same ozone problem, but a lot of them are very active as greenhouse gases. So they have, they're very powerful absorbers. I mean,
where do those come from? What are they used in?
Refrigeration, air conditioner, the same thing that the CFCs were, you had propellants, things like that. So the good news is that the concentration is still pretty small, but, in coming decades, if we keep using them, they could be noticeable. Another important is nitrous oxide. And one of the sources of this is from fertilizer. And so a lot of the protests, like in the Netherlands and Ireland and even Canada, related people trying to restrict their use of ammonia-based fertilizer so we don't have this nitric oxide pollution. Well, that's all very well and good, but we also don't have enough food unless we use a fertilizer. So that's causing, big problems as we speak. It seems pretty misguided to me. So there's other ways of dealing with that nitric oxide from fertilizer rather than just saying don't use it.
What are some of the other ways of dealing with it?
More chemically and how efficient application, and then more chemically related things. But it's a trace gas. I mean, it has a tiny impact, compared to CO2 or even methane. It has a tiny impact. It's not worth worrying about, in my opinion, given, the issues with CO2 and methane. So CO2 is the big one, and it's politically the important one.
Okay, yeah. So CO2 is the major greenhouse gas, and you said it's not reactive in the atmosphere, so it doesn't there's no chemistry going on there, or very little compared to methane. But it is a greenhouse gas, and it probably does contribute to warming to some extent. Can you give me an idea of what are the major sources, natural sources and sinks of CO2 that exist on Earth?
Well, volcanoes are the big one. Burning of, forest fire, burning of biomass emits a lot of CO2. into the atmosphere. I mean, those are the two big ones. The ocean has carbon dioxide in it. And, if you open a warm bottle of soda pop, there's a lot of fizz, the gas is escaping. Whereas if you open a cold bottle, you don't get that same escape. So certain regions of the ocean, there's a flux of carbon dioxide into the atmosphere, and other parts of the ocean sort of act as a sink of carbon dioxide. The biosphere, as it grows, as tree grows, they use sort of CO2 effectively as fertilizer. So when people talk about CO2 as plant fertilizer, I mean, it very literally is. It helps plants grow. So there's various geologic processes and seeps, where CO2 escapes. So there is natural processes where there is, variations in atmospheric CO2. And in very distant geologic past, we've seen periods with much higher CO2. That wasn't caused by humans. It was a whole host of complicated geological processes that were involved. So there are natural variations, but the emissions from burning fossil fuels have certainly, caused a spike. And right now our emissions are being subsidized by uptake from the land and the ocean, which helps diminish the impact of the CO2 emissions on the atmospheric concentration. So the question is whether those sinks are going to grow or decrease in the future. Okay, the signs right now show that both sinks continue to grow, but at some point, could that reverse? I don't know. But yeah, the whole carbon cycle, there's a lot of things that we don't adequately understand about the carbon cycle, and there's new things that we learn all the time. Like somebody identified, as an example, a bacteria in the ocean that seems to be sucking up a lot of carbon dioxide, rather than, the phytoplankton, they use carbon dioxide to grow. But it seems like this bacteria is also sucking up a lot of carbon dioxide, and that's something new. So I'm sure there's all sorts of new things that we will find out. But, we understand qualitatively how the global carbon cycle works. We don't understand the quantitative details. And the issue is whether the sinks are going to continue at the same rate or grow or diminish with time as we have more carbon dioxide in the atmosphere. I mean, that's the big unknown question.
And so if we were to substantially cut fossil fuel emissions such that CO2 levels went down measurably, how much confidence would you have that would likely or plausibly lead to the expected changes in surface temperature?
Well, the thing about the climate system is it has some very long time scales. And you really can't unring this bell, all the emissions that we've emitted. So some climate models have run the experiment. Okay, and they have all the fancy chemistry in the ocean and whatever. Okay, so if you immediately cut off the excess CO2 emissions and you run out the climate model for, a couple hundred years, I mean, after 50 years, I mean, there's no equilibration. Some climate models are still warming, others are cooling, and, there's no real equilibration. The things like sea level rise and the ice sheets have even longer time scales. So, that's hundreds to 1,000 years before all of that really equilibrates if we were to shut off the emissions. In terms of actually improving the weather and extreme events, it's even if there is a CO2 effect on all that, which I mostly question, you probably wouldn't feel an impact of that until the 22nd century. So, reducing the CO2 emissions, I think, is a good thing to take the edge off, some really catastrophic outcome. But thinking that we're going to quickly undo this and sea level rise is going to stop and the weather's going to suddenly be nice. No, that's not the way it's going to work.
When you think about global temperature changes and sea level changes since, say, the mid 1800s, where we have as good as data as we're going to get, can you just remind me, because again, this is my area and I don't even know, how much has the average temperature increased since then, and how much has the sea level changed since for the last couple hundred years?
Okay, the 1.1 degrees centigrade is what we're talking about since the end of the 19th century until nominally 2020. That's 1.1 degrees centigrade, which is about 2 degrees Fahrenheit. Okay. Sea level has probably, 100 years is about 8 inches. So that's more than 100 years. So it's probably a foot of sea level rise since 1860. Okay. And so, again, a lot of that sea level rise is natural, and some of it is probably associated with human-caused warming to some extent. But separating that out and trying to identify acceleration and filter out El Nino effects and whatever, it's not a straightforward thing to untangle. And now we rely on satellite altimeters to measure global sea level rise, and there's a ton of spatial variation, largely associated with ocean circulation patterns. So this is, and a lot of local sea level rise, New Orleans or wherever, is associated with the fact that the land is sinking. And it can sink for geologic reasons, or more likely it's sinking associated with land use, the sheer weight of cities, but also the extraction of groundwater and petroleum, oil and gas and whatever.
Wow, I never thought about that. Like the literal mass of cities pushes down the land.
Yeah, and especially the groundwater, it then compacts. Even if you stop doing the groundwater, there's no way to get that to expand again. So it just, what's done is done. So in most places, at least 50%, where sea level rise is a concern, more than half of the concern is associated with land use, subsidence. So, it's particularly bad, the Gulf Coast, the Galveston, New Orleans kind of area. And in the mid-Atlantic states, Chesapeake and around there is where you have a lot of subsidence. Florida, the state of Florida, which, half the state is under 6 feet elevation. Well, they have a sea level rise problem, but it's not really sinking. I mean, their problem is really associated with, the rising sea level. And of course, storm surge, which, from hurricanes, which exacerbates, but it's a slow creep. Global sea level rise is a slow creep. The concern about sea level rise is if there could be some catastrophic collapse of the West Antarctic ice sheet, because it's an unstable ice sheet. I mean, this thing could collapse and it would have nothing to do with warming. There's actually under ice volcanoes, and it's just a very unstable situation. Warming and raising of sea level, and that there's these ice shelves that extend out from the continent. And as the sea level rise and it's warmer, you're melting the ice from these ice shelves from below as well as from above. And once these ice shelves really start to move fast, and then the rest of the West Antarctic ice shelf, the motion would be accelerated. And so that's how you could, lead to collapse of some of the ice sheet. In the last interglacial, about 120,000 years ago, the West Antarctic ice sheet did not collapse. It appears to have diminished in mass, but it did not collapse. There's not a lot of uncertainty as to when the last time there was a pretty big collapse of the West Antarctic ice sheet. It's something that could happen. If it does happen, it's as likely to be caused by geological effects as anything related to warming. But that's the big wild card that has everybody, alarmed about future sea level rise. It's just a huge amount of uncertainty. And there's a huge amount of things that we don't understand about, the ice sheet dynamics of these marine ice shelves. So this is a very important and very active area of research, but there's not a lot of confidence in any of these dire projections of huge sea level rise in the 21st century. I mean, we're talking about most likely another foot or two.
Switching gears slightly, another topic I wanted to ask you about is just how you personally think about the different, why we might or might not use different energy sources available to us. So the way that I begin to think about this, so when people talk about like oil versus natural gas versus wind versus solar versus nuclear, like we have all of these potential sources of energy that we use in different ways to different extents. When I start to think about it, I think, okay, well, one key variable here, one dimension here is how abundant is the energy source. Another dimension is how well can we utilize the energy source given current state of technology? And then another one would be, what's the environmental impact? So, across those dimensions or any others that you think are important, how do you personally think about each of these energy sources and the extent to which we should be using more of one and less of the other and things like that?
Gosh, I feel like I need to pull up a table from my book because I lay out all these different things.
If you have it, you go for it.
Okay, hang on. I'm just going to look for a minute. Sorry.
Yeah, no worries. I was literally in my mind imagining a kind of a table there.
Okay. No, because then I won't forget anything this way because I put a lot of thought into this one. Book formatted, chapter 14. Okay. Okay, let me get to my little table here because I thought this was pretty clever. I have to find it.
Yeah, so for those just listening, in a moment, Judith is going to pull up a table. So you'll be able to see that on the video version, but we'll do our best to describe it verbally as well.
Okay. So again, the first thing is you want it to be abundant and cheap. I mean, human progress really depends on having, that not just, our safety and our daily whatever, but if we want to make progress and, build our economies and grow and thrive and meet our human potential, I mean, this depends on energy and we need it to be abundant and cheap. Okay, it also needs to be reliable. And this is, reliability relates to severe weather. Things that are dependent on the weather, tend to be less reliable. So, a question that I've asked is if, we're moving to renewables because of concerns about climate change and its impact on the weather, why are we banking on, unreliables, subject to weather variability and extremes? Another issue is energy security. And this is one that people sort of forgot about until Russia reminded everybody by invading Ukraine that we need to pay attention to energy security. Again, clean is another consideration. Pollution from emissions, mining, ecosystem and human health concerns, as well as CO2 emissions.
And did you find that table?
Yes, I did.
There should be a share screen icon at the bottom of your portal.
Share screen, yes. Host disabled participant screen sharing.
Okay, there you go. Try it now.
Okay. Share screen. Can you see my screen?
Not yet.
Not yet. Share screen. Okay, desktop. Share.
There we go.
Okay, here we go. Okay. So, and also is the issue of you don't want your energy source competing with food and water. I mean, it drives me crazy. The corn ethanol thing drives me crazy. I mean, it's some crazy percentage of the US corn crop is burned for corn ethanol, which raises the, a bunch, apart from raising the price of food. I mean, it's using water resources. I mean, it's degrading our soils, and on it goes. The other issue is there's an increasing desire for local control of the power sources. And this relates to, I mean, this is where home solar, is a big one, but also microgrids gives, community more control over their power. And the other thing is the land use issue. I mean, all these, wind farms and solar farms, not to mention primary biofuels, use a huge amount of land. And this is, interfering with other land use priorities and also with ecosystems. Okay, then we have another issue is material use. Again, relates to the scarcity of rare minerals, scope and scale of mining, supply chain issues, and then no CO2 emissions. So when we're envisioning what we want for a 21st century energy systems, these are all the things that you would consider, at least in my mind. And I think we need to decouple the energy issue from the global warming issue, because the urgency associated with the climate change issue drives us in a single direction to use available technology and to implement it quickly without really doing full life cycle assessments of the resource use and even emissions associated with some of these things. In most countries, the land use is prohibitive for, relying on wind and solar. They just don't have the land for it. The US, Canada, and Australia and Russia, they have plenty of land, but a lot of European countries and East Asian, Japan, South Korea, they just simply don't have the space. Of course, there's offshore, but that's, the coastal shore region is also valuable as well. So there's a whole host of things you want to consider. There's a lot of reasons to transition away from fossil fuels, apart from pollution and CO2 issues. First and foremost is that it has to be continually mined, as opposed to renewables and nuclear. I mean, once you have the thing built and running, you don't have to continually, mine for fuel on a daily basis. This introduces, cost spikes and variability, geopolitical concerns, a whole host of things. So there's reasons to transition away from fossil fuels independent of the global warming issue. When I look at, when I try to imagine what the power systems look like in 2100, I mean, I don't see a planet covered in windmills. I mean, I don't see how we can do this without nuclear power. I mean, in order to make progress, we need power density. Wind and solar are two they're very diffuse sources of power. I mean, I don't see this without nuclear power. Geothermal would be great, but we're not quite there yet in terms of figuring out how to really, that there's advanced geothermal and it's not clear, exactly what this means and how it will play out, but that seems like another great power source. I think rooftop solar is a great solution that helps, with the personal autonomy that people desire. I think wind makes sense, in the Great Plains of the US. I mean, where there's, just nothing there. I mean, in certain regions, wind power seems okay. I think bioenergy, we need to get away from that. I mean, the US is crazy with its, corn ethanol, but in Europe, they're actually burning wood chips, in their power plants. And, they're importing wood chips from the North Carolina forests, and they're clear cutting forests in Canada and shipping it over to Europe to be burnt, because this is renewable energy. Well, it's renewable energy that's destroying our ecosystems and is also emitting a heck of a lot of CO2 into the atmosphere. It makes no sense. So, the bottom line is what I like right now is nuclear, geothermal, rooftop solar, and I think wind has certain niches, but who knows what the future holds for new energy technologies. But, here's the checklist that I think you want to, look at when you evaluate these individual energy sources. But the underlying thing is abundant, cheap energy. And this is what we need. In the developing countries, people fear, in developing countries, they fear a lack of energy and the inability to grow the economy much more than they fear climate change. And then developing countries, particularly in Africa, they don't have access to grid electricity. And they're even though they have a lot of natural gas resources, they're not receiving loans or anything or assistance from World Bank or whatever to help actually utilize those resources. Rather, they mine them and then ship them off to Europe because Europe has a capacity to use them. So it's really exploitative. Been referred to as green colonialism, energy apartheid, and I've been very vocally against that strategy for trying to reduce CO2 emissions by keeping Africans in poverty. I think it's neither moral nor just. It makes no sense. So again, I think energy abundance first and foremost, and while we're at it, let's work down the list and see what makes sense in terms of, each region and each economy is going to have, different resources and different needs. And so there'll be a lot of different solutions in different locations, but this is the way I see it playing out, where CO2 emissions is not the primary determinant. Like I said, moving away from fossil fuels, I think that's going to happen anyways. But in terms of what next, there's a lot of other considerations to be thought about.
I see. Yeah. So you've got, for those just listening, we're looking at this table, and there are all these values, as Judith is calling them, that each have their own risks and dangers. One is the abundance of the energy supply. One is the reliability of the energy supply. How secure is it? How clean is it? How does it affect our food and water supply? How does it give or take away people's local control of the land? Is there minimal land use associated with it? Is there mineral material use? And then CO2 emissions. So there's all of these factors that go into a matrix of considerations with respect to each of these energy supplies. And Judith, how would you summarize what you just said? It sounds like basically you like nuclear energy. You think that's a way to move. You like wind for, the niches of the world where it can be used and there's enough wind and not a lot of other need to use the land. And you think we're going to move away from fossil fuels anyway, not just because of the CO2 emission side of the equation, but because there's a variety of other reasons to move in other directions as well.
Yeah, and I also like rooftop solar. I'm not a fan of the big solar farms because the land use is crazy for solar farms. They're even less dense than wind turbines. But rooftop solar, I think, is a fabulous solution. It doesn't add to the land use problem, and it helps promote the local control issue.
I see. Yeah, that makes a lot of sense to me. I know that one of the criticisms of a lot of those big solar farms is that they just take up so much land, and there's not a lot of bang for our buck there, especially when you consider what other things that land could be used for, such as food.
Exactly.
And on the question of food, this is another thing I'm certainly not an expert in, and a lot of people seem to have very strong opinions here. So, when we think about land use for food production and how this ties into, climate-related externalities, you get some people arguing that we shouldn't be farming animals anymore because that's associated apparently with more CO2 emissions. Other people say, well, yes, no, maybe so, but when you have large swaths of land devoted to, these plant monocultures, that has a lot of its own issues to do with, destroying local wildlife populations and increased use of pesticides and things. How do you think about land use in terms of food and how it ties into how we should think about food production as it relates to the effect on the local climate and the local environment?
Well, the intensity of food production relative to the amount of land has increased substantially in recent decades. So we're getting a much greater yield per acre. And, that trend, is continuing with better farming practices, better hybrids of crops and whatever. There's a lot that can be done for smart agriculture in terms of, better serving the land, and increasing yields. And again, one of my clients is an NGO working in South Asia to help farmers make better use of weather forecast information so they can plan how much to plant, when to plant it, when to fertilize, how much to fertilize, when irrigation is needing, when to yield, when to harvest, which helps them increase their yields and reduce their risks from adverse weather, both seasonally and on a weekly basis. So there's a lot that can be done to minimize fertilizer use, to make farming more efficient. There's many things that can be done to make agriculture better with regards to animals, cows and whatnot. They can help the land, by grazing, can help the land, and there's ways to make this better. I don't see people giving up meat for the sake of CO2 emissions. I don't see that happening. That there's ways to manage the land so that the soil stores more carbon. And again, there's better farming practices that can be used, and there's a lot of research on this. But at the end of the day, the biggest problem is food waste. There's a crazy amount of food that gets wasted. In my own household, I solved that problem by feeding our chickens any meat, fish, vegetable, fruit, kind of nut seed scraps to the chickens. And so they recycle that into eggs. So we have very little food waste at my house. But, globally, food waste is just crazy. And so if we figure out ways not to waste so much food, that would be, a big solution rather than trying to convince people not to have livestock and not to eat meat. I don't see that as happening.
So, I mean, as a climate scientist with your background and your expertise, and just a human being living on the planet, if you were to, if we could just wave a magic wand and Judith Curry is the CEO of Earth, what specific concrete actions would you have policymakers implement to, you know, optimize for human well-being with respect to energy usage and minimize some of the negative consequences of using different energy sources? What would that look like in the near term, the next 5, 10, 15 years? What should we be doing, and what should we stop doing? And, you know, all of that within the domain of like what's actually implementable with the technology we have today.
Okay, I strongly support transitioning to a 21st century energy system, that's more abundant, cheaper, cleaner, whatever. Okay, we want to do that transition. But in order to get there, we need lots of research and development. And we're also going to need a lot of fossil fuels in the short term. I mean, how are you going to build the nuclear power plants and the big wind turbines and do all that mining and everything without fossil fuels and the machines that are fueled by fossil fuels and the mining and everything? So we just need to accept that we're going to need more fossil fuels in the short term. And once we accept that and stop trying to kneecap the fossil fuel companies, with all these silly things, canceling pipelines and divestment and no loans and all this kind of stuff, we could get on with the transition. Okay, having abundant energy right now so people aren't suffering, but we have enough energy to actually, build this new system and all these new, power plants and whatever. So we need to drop the for the next 30 years, we're going to be using fossil fuels. So we need to get over it and not try to tie ourselves to these timetables with CO2 emissions and whatever, which, we're not going to get anything accomplished. And then we need to, the next thing on the list, we've got energy, water, and food. Those are the three big ones. Okay, we need to manage our water resources better. I mean, oftentimes we're faced with either too much or too little water. We need to, figure out how to deal with floods, even big floods, and we need to do a better job of water storage so we're not faced with these, crises. And once we have, really abundant energy, we can do desalination, with coastal plants. So abundant energy will really help us, adapt to climate change. Everybody can have air conditioners. We can have, at least the coastal regions, we can have, abundant water with desalination, things like that. So deal with water and then deal with food. There's better agricultural practices that, protect the land. There's smarter agricultural practices that can be enabled by, better use of weather forecast information. There's new hybrids, varietals, that will be more robust to whatever, the weather situation turns out to be. So, dealing with energy, food, and water as issues in and of themselves, forget the climate and CO2 for the moment, but just figure out what we want our energy, food, and water systems to look like for the 21st century to provide security, abundance, and so that humans can develop and progress and realize our potential in the 21st century. So that's what I'm looking at. We need to just drop the focus on CO2 and focus on these other things, and the CO2 will, take care of itself. And if it really turns out to be a big problem, we don't understand the magnitude of the problem we're facing in the 21st century. It could be relatively benign, or there could be some, crazy things happen that we don't expect. But if we're prosperous, we can increase our resilience so that we can handle whatever nature dishes out at us. So energy, food, and water, and then resilience against extreme weather events and whatever climate surprises nature might throw at us. I think that's what we should focus on. And if we stop talking about CO2, we can get on with some of these things and make real progress. And if CO2 really turns out to be a bigger problem than we think, then we can deal with direct air capture and, whatever other kind of things we might try to do to sequester carbon dioxide. But in order to do that, we're going to need a lot of energy and a lot of land for direct air capture. So if that's all used up by wind turbines, whatever, this is all competing against each other. So, it's a complex issue, but energy is at the linchpin for all of our, telecommunications, transport, logistics, everything that goes on in the world is, underpinned by energy. And we can't sort of kneecap ourselves by trying to play games in the near term with trying to restrict fossil fuel use. It's just going to do way more harm than good, and it's going to slow down the eventual transition to what will eventually be a cleaner energy system and perhaps an agricultural system with less CO2 emissions.
Yeah, on the subject of extreme weather events and being resilient to these sort of high magnitude, low frequency disasters that can happen with, the climate and geological phenomena and things, are there any kinds of extreme weather events or geological events that you're particularly concerned about, or you think we're particularly underprepared for compared to others?
Well, things having to do with floods, hurricanes, storm surge, and flooding, river. I mean, these are the ones that are the most devastating and where the most lives are lost and the most damage is done. So, storm surge, you can do natural coastal protections, engineered barriers and all this kind of stuff. And the Dutch are certainly the experts to those kind of barriers. Actually, and part of it is really zoning. We're developing too much on the coast and in floodplains. So if we're going to build in those areas, it should be cheap stuff, with a lifetime of 20 years, that you're going to expect it to be destroyed at some point. So we just need to either stop, like Florida, I mean, the whole state, is a potential disaster zone. But I understand the appeal, of that climate and the beautiful coast and everything like that. So you're not going to say, don't live in Florida because, you're going to get blasted by sea level rise and hurricanes, but you can build structures, that are elevated so they don't get so impacted by storm surge and sea level rise, or you can build really cheap stuff. So when it gets blown down, you just rebuild it, at relatively low cost. So I think water, too much water, floods and river floods, and but the river. I mean, you're going to farm, in river basins and flood-prone because that's just the richest soil. But you don't need to have whole cities there. So I think better zoning and discouraging, building in floodplains. Okay, is an important thing to do because a lot of these people, that their places get knocked down by hurricanes or wiped out by a flood, and then they get funds to rebuild, and the same things happen. I guess that there's some area in Louisiana where a lot of the structures have been rebuilt 12 times in the same location, and they keep getting wiped out. Now that makes no sense. We need to stop subsidizing that kind of behavior. So this is what I think the big disasters are, like heat waves and cold waves, if you have adequate energy supplies, these are non-problems. But it's too much water is the big problem. These big floods that can be horrendous, to me, are the biggest problems.
And can you go ahead and close out the screen share? There we go. Obviously you're no stranger to the politicization of science and how polarizing, climate science is. So, one of the most interesting and upsetting things about climate science is, you can pluck a random person out of the population and you can have a very good guess as to, what their views are going to be based purely on how they vote politically. And I'll assume that most listeners are not going to be unfamiliar with that with respect to climate science. But, even more generally, in your view, and based on your experience in this whole climate science, controversy that it's been controversial and polarizing for a long time, what is it about certain fields of science that makes some of them more prone to politicization than others?
Well, if it's policy relevant, the one thing that's worse than climate change seems to be gender and GMOs. I mean, people are even more passionate about that kind of stuff. The issue, the problem with climate, and this one is unnecessary, and it was done by, it was trying to oversimplify the problem to meet with a pre-planned political agenda, trying to push this dangerous anthropogenic climate change and that we need to, eliminate fossil fuels. And this was decided on, in the early 1990s before we knew much of anything about this problem. So we had the policy cart way out in front of the scientific horse. And people just, the scientists were told to build a consensus around this, to provide enough certainty so the policymakers could proceed with this. And this is like the totally wrong way to make policy, totally wrong way to let science do its thing so we can actually understand this problem. And so you ended up getting a lock-in, in terms of the policy and the science. There was so much inertia, heading in this direction. And then, at some point, say in the last 5 years, people realized, well, this isn't really working. We're not accomplishing much. We've got this huge amount of political polarization. Emissions are still increasing. The public is at war over this. The science has been framed too narrowly, and even corrupted in some instances by this whole thing. And, this is not healthy for science. It's not healthy for policy. It's not healthy for humans who want to move forward in the 21st century, with a better situation, clean environment, more energy, on and on it goes, so that they can really, develop the full human potential to thrive. So we're stymieing progress, human progress, as well as stymieing progress on actually reducing CO2 emissions. We're putting in a lot of windmills and whatever, but it's not displacing fossil fuels at this point. Fossil fuels are still like 82% of whatever, and most of the clean stuff is hydropower or nuclear. It's just like a tiny amount of wind and solar globally. It just isn't. It seems like a lot, but in terms of the overall energy that we use, it's just like a sliver. So, this isn't working. And the politics of fear, trying to scare people into doing something about climate change, I think has backfired. And the most interesting thing about this Inflation Reduction Act, that recently passed the Senate, is that it wasn't billed as a climate change bill. It was titled with something else. There's a lot of incentives for people to do various things related to clean energy. So it's more of a carrot rather than a stick. So they're trying to And there's also stuff in there for fossil fuels. It's really about energy abundance and trying to provide people with incentives, to go towards cleaner energy sources. And, this was a political winner, far more than the carbon tax and cap and trade and, the punishing of the oil companies, all these other things that have been tried that haven't worked. I mean, this one seems like a political winner. Don't call it climate change and give people carrots rather than sticks. I mean, that seems like the winning recipe. So, I mean, maybe we can make some progress here, but we need to get away from this arbitrary deadlines of emissions. Oh, we can't build a new gas power plant because of CO2 emissions. Well, if you don't build that gas power plant, you may not have enough energy to build your renewable energy. And you're going to have, people don't want to pay more money for energy. We've seen this everywhere, in Europe, the US, and the poor countries like Pakistan and whatever, they can't afford to pay these high gas prices, and people are, just really suffering. So not having enough energy is very, very bad for humanity. We need abundant, cheap energy. And if we can make it clean, great. But we don't try to cut off the tap before we've accomplished the clean energy infrastructure. We need fossil fuels until everything's in place.
And on this on the subject of the politicization of science and how and why the science is conducted. So, in your experience as a climate scientist, how does something like scientific funding and how it's allocated and doled out influence or set up incentives for scientists to seek out certain conclusions versus others? How does the way that science gets funded in the U.S. at least start to relate and shape the types of results that people go out and look for?
Well, yeah, it's really the funding agencies issue announcements of opportunity that are framed around helping us to address the climate crisis. And on it goes, and so like you've already presuppose a conclusion. The most, even the National Science Foundation, which isn't, supposed to be mission oriented, it frames a lot of its announcements, related to human caused climate change. And it's very, and the main problem is that natural climate variability has been marginalized. I mean, NASA is really good at funding the solar research. So, kudos to NASA on that one. But like the natural climate variability, the ocean oscillation, that gets just a sliver of funding from, the oceanography division at NSF or something like that. So that there's basically no funding, for this, which is a problem. And a lot of the really interesting work that isn't, along this mainstream narrative comes from people from outside climate science and even outside academia. In fact, some of the most important research on climate sensitivity is being done by Nick Lewis, who is a British semi-retired British financier who happens to know a lot about math and statistics and majored in physics and math, I guess at Cambridge or something. But he doesn't have a PhD and he's not an academic, but he's doing what I regard to be the most important research on climate sensitivity, as an example. And again, like I said, I'm reviewing a book right now written by a molecular biologist on the sun climate connections, so it's coming from a very different, and neither of these people have like government funding for what they're doing. It's just being done off of their own interest and their own passion. So, it's a sad state of affairs that some really important science is just getting completely neglected because the whole climate change issue has this narrow frame around it that, it's all about dangerous anthropogenic climate change. And so everybody's searching for, and it results in what I call climate model taxonomy, where people look at the output of climate model and say, oh no, we aren't going to be able to grow wine in California in 2200, this kind of stuff, which is way beyond what the climate model can support. But then the person gets, headlines and a lot of positive career reinforcement just to do this rather silly climate model taxonomy. So we've sort of, climate science has become this diverse field, academically. Like I said, back in the day when I was a graduate student, climatology was a subfield of geography. Now you have whole colleges of climate studies, which integrates human systems and social justice. And they may learn a smattering of actual physical climate science, but it's become this very broad issue incorporating politics, economics, many social science fields, which is good, but it's very hard. But they're all presupposing all this, that we understand the climate system and we know what's going to happen, and it's dangerous. So all of this is built on, presuppositions that we frankly don't have all that much confidence in.
Well, Judith, as we start to wind down here, do you want to maybe describe for people the book that you're writing and what it's all about and why you chose to write it?
Okay, the book that I'm writing is Climate Uncertainty and Risk. And it's being published by an academic press, so it has to pass academic muster and lots of references and everything. But I'm also trying to write it so that it's understandable by anybody with a college degree that has some background knowledge about the climate issue. What I'm trying to accomplish is to reframe this, it's really the politics of uncertainty, if you will. I mean, that we really don't know what's going on and that we need to make decisions in a different way rather than trying to speak consensus to power, having scientists negotiate a consensus and then send it off to the policymakers and say, do this. That's not what we should be doing. We need to treat this as a systemic risk management problem with many dimensions, that there's no silver bullet solutions. I mean, the best we can hope for is to carve off little pieces to make progress. This is a climate change generally. It's a problem that humanity has lived with since, its inception for tens of thousands of years or however long, and that it will continue to be a problem. And that we need to not treat this as a scientific problem, but as a human problem, and that the decision-making and the policy space needs to be opened up, and try to find, a much broader range of solutions to little pieces of the problems that we carve out, and to treat this as a risk management problem, and to use some principles from decision-making under deep uncertainty. And a lot of this is to focus on the solutions and try to get agreement on the various solutions rather than getting lost in arguments about what's causing the problem. Like, people can agree on maybe what are the parameters for a 21st century electric power system to look like. I mean, maybe we can agree on that, but we're going to disagree on, if it's tied up in climate science, we're going to disagree on the motivations and the magnitude of the problems, and we're going to get lost and never get to the actual solutions, which people might have agreed on without even thinking about climate change. So the book, it's a message of, we want to promote human prosperity, flourishing, thriving in the 21st century. And this includes, not just for the developed countries, but first and foremost, providing these opportunities for developing countries, particularly in Africa. It's something that's a moral imperative, and that there's a lot of tools in the policy making arsenal and risk management and decision making under uncertainty that we can bring to bear to this problem to make some sensible decisions that, by the way, will make us less vulnerable to climate change. The extent that we can actually manage CO2 remains to be seen. I don't know that we can. And also the extent to which increasing CO2 is really going to mess up our climate in the 21st century relative to whatever natural variability dishes out. That also remains to be seen. So there's a great deal of uncertainty all around, but we can use this uncertainty to help us think outside the box and come up with some better solutions that have broader buy-in from the affected people. So that's what I'm trying to accomplish with the book. The first part is more about the philosophy and politics of science. The second part focuses on what the climate might look like in the 21st century and how uncertain it is. And then the third part is really about risk and response. So it covers some pretty broad territory, but I think it's designed for if somebody who didn't know me or wasn't, they would have a hard time. They would read this book. This is my goal. They wouldn't know where I stand in the debate, whether I'm on the right or the left or, denier or alarmist or whatever. My idea is to, present the perspectives, and rational people can disagree, about a lot of these things. So I try to really take a centrist, acknowledging the debate, acknowledging the uncertainties, pointing out both sides, how they've made the situation worse. So I'm trying to present a very even-handed analysis and a framing for how we can move forward on this issue.
Well, Dr. Judith Curry, I think that's a good place to end it. Thank you for your time and everything that you shared with us today. Any final thoughts you want to leave people with beyond what you just described?
Not really. I think, we have, let's just look at this as an opportunity to move forward in the 21st century rather than a hair shirt that needs to, to be born, and that we need to, punish ourselves and restrict ourselves, so that we don't increase CO2. We need more carrots and fewer sticks in order to make progress on this.
All right, Dr. Judith Curry, thanks again.
Thank you.